Hi, my name is Sayge Barkley, and my research project this year was on the development of bioplastic from feather keratin, and I am from Baker High School. My research was conducted in my high school laboratory. The feathers were provided by the Rost Ranch, and the chemicals were supplied by Baker High School. Linda Rost was the supervisor on the project and was very helpful in developing procedures and analyzing data. So let's start with a brief overview of plastic and its effect on this planet. What is plastic? Plastic is polymers of carbon or hydrogen. There are many different types, but all have a certain degree of strength and are all lightweight. Some examples are PVC, polystyrene, etc. It can be molded into limitless shapes or stretched into fibers for other materials such as polyester. It has many uses from medical packaging to clothing. So there's much plastic waste on this planet. 2 million plastic bags are used every minute. 500 million plastic straws are thrown to waste per day. Not all plastic is visible also. Some has been reduced to small particles in water and land systems. If the rate of plastic dumping in the ocean continues, by 2050 the mass of plastic in the ocean will exceed the mass of fish. This is a quote from the Ellen MacArthur Foundation. 300 billion more plastic bottles were sold worldwide in this decade than the last. Earth's equator could be wrapped around 10 times by the amount of bubble wrap made per year. However, there are many advantages of plastic, which is why it can't be gotten completely rid of. It increases freshness in packaged foods and helps prevent contamination. It's used extensively in the medical industry, and electronics have been revolutionized by the use of plastic. It's also perfect for use in appliances because of its lightweight, strong, and malleable properties. However, it comes with disadvantages. So during production, plastic comes from fossil fuels, and chemical processing plants that emit large amounts of pollutants are necessary for its production. And post-production, chemical additives from the plastic can seep into the water systems, and landfills slow the decomposition process. So there's a very large buildup of plastic. Recycling is cost ineffective, and pollutants are released during the process. What is bioplastic? Bioplastic is a biodegradable plastic made from biological substances rather than petroleum. In this study, the substance being used is feather keratin. So large-scale chicken farms produce 90% protein waste from feathers. The goal here is to chemically extract keratin from feathers and combine it with glycerol to form a plastic. My purpose was to optimize bioplastic production from feather keratin and observe the strength and properties. My null hypothesis is there will be no difference in the mass, texture, and physical appearance of the different bioplastic types. My alternative hypothesis is there will be a difference in the mass, texture, and physical properties of the different bioplastic types. My independent variable was the new bioplastic feather keratin protocols and the type of keratin extraction procedures. My dependent variable was mass and texture of the keratin and bioplastic, and my control was the original bioplastic feather keratin protocol. And constants, feathers, solutions, and heating methods. So part one of my procedures was the keratin extraction. This was the most difficult part of the process. Feathers from a local farm were boiled and dried to clean. Barbs were cut off the quill in small pieces. Feathers were then degreased by covering them in petroleum ether, and once that evaporated, they were added to a solution of sodium bisulfite, SDS, and urea. The solution was stirred with a magnetic stir bar on a hot plate. The solution was then centrifuged and filtered. It was rinsed in dialysis tubing, as you can see here, and placed in the water to remove the sodium hydroxide. The water was changed out every day until the outer solution had a neutral pH, and the dialysis tubes were then rinsed in hydrochloric acid with a pH of 1 to clump the keratin together. It was then poured out of the dialysis tubing and left to dry, and this is what here is drying on parchment paper. That right there is the keratin solution. Part two was my bioplastic. I dissolved the keratin powder in sodium hydroxide. I then combined this with glycerol and mixed it with a magnetic stir bar on a hot plate. It was then spread in a petri dish and put in an oven, and this was the resulting prototype of bioplastic. Part 3 is the tilapia keratin bioplastic. I combined capsule keratin with an equal amount of sodium hydroxide. I added 10% glycerol, and then I repeated with 25%, 75%, and 100% glycerol. I mixed with a magnetic stir bar, poured each solution into petri dishes, and put it all into an oven. Here are my results. So there were 4 batches of feather keratin. Batch A was a filtered sediment, so I did use the filter paper, and I could not find a way to recover it after the liquid was evaporated off, so my yield was 0. Batch B, the filtered sediment, was used without filter residue, and I got 0.1359 grams. Batch C was rinsed but not filtered, so I got 0.0736 grams. And batch D was rinsed, not filtered, and it was rinsed in acid. And I got 0.1772 grams. So my feather keratin bioplastic, the prototypes were both made from batch B. I made this one with microcrystalline cellulose. Its consistency was tacky and did not hold a uniform shape, plus there was like bubbles in it. It was easily pulled apart and it needed a binder. The yield was 0.0520 grams. Prototype 2 was also made from batch B, as I said. It was also made with microcrystalline cellulose. I used a greasing agent to try to get it off of the petri dish easier, and it made no difference. It was very flaky and did not hold together, as did the last one. The yield was 0.1707 grams. So the tilapia keratin bioplastic, 5 prototypes were made. I made a control without any of the feather solution, or without any of the tilapia keratin solution. I made a 10%, 25%, 75%, and 100% glycerol. The control was the same as the 10%, but with no feathers, as I said. 10% was dry, crystallized, and flaky. The 25% was the most successful. It was not flaky. It was viscous, but not as much as the 75% and the 100%. The 75% was viscous and did not hold together, and the 100% was the same. Here is a picture of each. There's my control, 10%, 25%, which I said was the most successful, 75% and 100%. You can see how these are both viscous. My conclusion, I rejected the null hypothesis. Each had separate characteristics. Feather keratin procedures did not produce enough keratin to make a large enough bioplastic sample and to test biodegradability, which was the original goal. Also, extracting the keratin proved very difficult. This is why focus was switched to the tilapia keratin in the capsules. The feather keratin bioplastic was flaky and thin, and the best tilapia keratin bioplastic was, as I said, the 25%. However, it was still very tacky. Future research is needed for different bioplastic sources and recipes to create a strong and malleable prototype. Here are my resources. Thank you. Awesome. That was 9 minutes and 17 seconds. And then we can